Hello, friends. This is a video on the Schwarzschild, I think that's how you say it, metric, and time dilation. But it's actually more about space and time. I'm going to go a little farther in depth. This is what we're doing in class on Wednesday for B period, Thursday for X period, before your weekend homework. Weekend homework's fun. It's kind of cool. It's about how space-time is a river. And that's what gravity is. And that's like what's really happening. Oh, that's kind of cool. Or it's a way to look at it. Anyway, I'm excited. This is kind of fun. So we have the Schwarzschild metric. Get that. RZSCH. Got it. Metric. What is that? Remember that. And it only goes to the surface of an object. Because if I have the Earth and I drill a hole into the center of the Earth, right? The only, say I'm here, the only, or say I'm here, the only thing that affects the force of gravity is the internal mass. This is something called the shell theorem. Don't overthink it. But the point is that we still use the Schwarzschild radius of the Earth, 0.0089 millimeters, even if the object isn't a black hole. So the Schwarzschild metric works up until the surface of the object. Now, what's cool about a black hole, so the point is, as I go deeper, deeper down, less mass is working on me to exert gravity. So a way to look at that is, say I'm here, at a point internal to the Earth, then I'm actually being pulled up because all the mass of the Earth is attracting me. So I'm being pulled up by these forces here, which are strong, but I'm being pulled down by these forces here, which are weak, but there's more of them. So it ends up canceling, and all that ends up mattering is the mass that's internal. This is a somewhat it's not non sequitur. It's important, but it's like, don't overthink it. I just wanted to say that's a thing. So those of you who are wondering, why are we using the Schwarzschild radius for the Earth when it's not a black hole? Well, it's still a representation of the gravity, because remember, if the Earth were a black hole, every orbit would stay the same. Our gravity would still be 9.8 right here. We would just fall because there'd be no surface. So a black hole has no surface. It is a singularity. And in space, there's this Schwarzschild radius, which is just space. It's the event horizon, where the escape velocity is the speed of light. And our goal today, tomorrow, and over the weekend is to interpret this in terms of general relativity. What does this mean? That's a big deal, and it's eye-opening. It's a third eye opening in terms of our realization of what is going on. And we'll do some meditations that really get to like the four-dimensional. We can do it. We can visualize the four-dimensional landscape of space and time and gravity, of existence itself. It's remarkable. So take this slow, but just dive in. So we have a point in space, we have a sphere in space, but all the mass is at the singularity. So everything is internal. So when we go into a black hole, there is no shell. This is called the shell theorem. This doesn't apply. Schwarzschild metric works up until the surface. For a black hole, there is no surface, so it works all the way to the singularity. And that's what we're going to do today. We're going to dive into the singularity. We're going to go into a black hole today, in theory, and see what the Schwarzschild metric says happens. And over the weekend, we're going to interpret it in detail. And next week, we're really going to interpret it. And it's going to be the coolest. This is so fun. So you guys are ready for this? This is the best. Breathe. Breathing is essential to go through the four-dimensional landscape. It's like the dance of existence. So if you go through the fourth dimension of time, right, This is the speed of light times time. You want to breathe in and breathe out. Will help you go through. That's why dancing is so cool. That's why we feel timeless when we're moving. Because when we're moving, we're flowing with time. When you try to freeze time, you actually feel it, right? You don't, it's not timeless. Now, meditation's great, but you notice when you're meditating, you're doing slow, purposeful breaths. And that can awaken that. See my little tapestry right here, that third eye connection with the breath and the heartbeat, right? Is that four-dimensional landscape. We're moving through the fourth dimension of time. The breath will help you do that. So we'll connecting with your heartbeat. So you can stay in that moment. The Schwarzschild metric describes how space and time are changed in a gravitational field. In other words, next to a mass, technically next to anything with energy. Technically, you can make a black hole with light itself. That's nearly impossible to do, meaning it would take an absurd amount of light focused on a very singular point, because light can collect. So you'd have to focus an unreasonable amount of laser beams. We could do the calculations, but if you did it, light itself could form a black hole. Let that bake your brains for a second. Energy warps space-time. Here's how. So we have ds squared equals c squared dt squared. Remember, this is the observer inside the black hole, or inside the Earth's gravitational field, or inside a gravitational field. This is the inside observer. And remember, space is time. Time is a fourth spatial dimension. So we can write it as ds, which would be meters, or dt, which is seconds, and c, meters per second, translates the two. Same thing. Amazing. So how that is warped is by this Schwarzschild element, we can call it, the Schwarzschild factor. Schwarzschild radius over r, 1 minus that. Great. We already mapped this in class. As r goes to 0, it's flat space. As r goes to infinity, it's flat space. This goes to 0. I gotta breathe, right? As r goes to 0, this does something very strange, as we're gonna see. Anyway, dt prime squared is a flat space-time observer minus dr squared over the Schwarzschild element, or the Schwarzschild term. Great. This is our Schwarzschild metric. We're ignoring, we're setting d omega equal to 0. So it's only radial motion. So remember, dr is the change in radius, inward or outward. Here's the Schwarzschild metric. Sorry, there's a c squared here. I keep forgetting that. Anyway, let's do it. So what I want to do is this. Of course, if we're at rest in space, notice how I have to say that. That means that dr is 0. Which means that we should get dt equals the square root of 1 minus rsch over r times dt prime. If you just plug in dr is 0 here and you solve for dt, you're going to get that pretty quickly. This is gravitational time dilation. We did this in class before, and we calculated the time dilation for GPS satellites and our own time dilation. Gravity makes time go slower, closer to more massive objects. That's the extraordinary first. There's many. The first of many extraordinary realizations of this theory, and it's real. Right? You can take an atomic clock and you can measure it. And people have done that. That's so cool. So what I want to do today is do some calculations with this and go inside a black hole and realize something's up. When I say go inside a black hole, I mean inside the event horizon. Because remember, there's nothing there. It's just space. Everything's at the singularity. I want to examine that. So we're going to dive into the event horizon of a black hole. So let's apply this. Question 1. Let's say dt prime is 80 years. I'm arbitrarily picking it. I picked 23 in class. I'm going to do 80 just for fun. Which means the outside flat space-time observer experiences 80 years. So the rest of the universe is experiencing 80 years. How much time do we experience? Well, let's say, actually, let me say that straight up for all of these examples. Let's say we're at r equals twice the Schwarzschild radius. It doesn't matter the size of the black hole. All that matters is where you are relative to the Schwarzschild radius. Obviously, the size of the black hole will determine where that is. But let's just do everything in terms of the Schwarzschild radius for simplicity. You'll notice you plug that in. dt equals 80 times the square root of 1 minus rsch over 2 rsch. So we get 1 minus a half. Square root of that is root 2 over 2. So 80 times root 2 over 2, which is 80 times 0.7. I'm going to do this exactly on my calculator. And I get, times 0.7 would be 56 on the nose, but it's 0.707. So 0.5657 years. That's pretty cool. So if you hung out near a black hole your whole life, everybody outside would age 80 years and you would only age 56. So it's a way to time travel. So there's 2 ways to travel forward in time faster than everybody else. One is you go really fast, twin paradox. 2 is you hang out near to a strong gravitational field for a while. You come back, everybody else has aged longer. It's amazing. Right? So now let's get closer. Say we hung out for that amount of time. From the outside perspective, that amount of time at 1.05 the Schwarzschild radius. Now we're getting close. So we're going to talk about what happens at this close in other contexts, but in terms of time dilation, now we're going to start to see significant effects. 80 times the square root of 1 minus rsch over 1.05. And that equals 80 times the square root of, well, 1 over 1.05, 1 minus that, is the square root of 0.0476. Square root of that times 80, I get 17 years. What I marvel at that I want to focus on is, first of all, this is significant, 80 compared to 17, but we're still on the order of years. It's not like I hung out there for an hour and the rest of the universe fast forwarded a century. And we're now 5% out of the Schwarzschild radius. We're really, it's still too close to the point of no return, you might agree. And if we calculated the force it takes to sit here, again, it depends, remember, on the size of the black hole itself. Spaghettification occurs more for smaller black holes, ironically, because gravity is more compact there, whereas the density actually decreases for larger mass black holes. The Schwarzschild radius is farther out. Either way, if we're 5% out, we're going to experience 17 years compared to 80. Cool. Just fun calculations, somewhat picking random numbers out of a hat. 3. We got to do it. What if I'm at the event horizon? Now, something obvious happens here. Mathematically, at least. I get 0. Now, what's interesting is this is a reference frame sort of trick where we're going to talk about this more in class. I'm going to sort of say this quickly. There's two ways to interpret this. One is from outside, it appears that the inside observer experiences no time. If you're actually crossing the event horizon, remember, it's all relative. Time, your clock is ticking normally. It's all relative. So if you are the inside observer and you're at the event horizon, say you're at RSCH and you're sitting there, what would you see? This is the interesting point. That dt prime compared to dt goes to infinity. So 0.1, from outside, it appears that the inside experiences dt equals 0. We're going to talk about that. So if somebody goes into a black hole, anything that goes into a black hole appears to be frozen on the event horizon. It's, so flash a smile, it's literally for infinity time written on the event horizon as information. And that solves something called the information paradox, if you've heard of that, that every piece of information of something going into a black hole is written on its event horizon, which brings a whole new meaning to the word event horizon. That all of the events of anything going into it is written on that surface. So it actually becomes an information surface from an outside observer. Now be careful, going into the event horizon, you don't notice anything unless you're spaghettified. You might notice that. Tiny detail, asterisk. Unless it's a big black hole. But if it's a big enough black hole and the tidal forces, this is what they're called, aren't significant enough, you will actually not notice yourself going into the black hole until you turn around and realize that the entire universe has fast forwarded in front of your eyes and infinite time has elapsed. Which means from the inside, from you, this is the inside observer, dt prime goes to infinity, which means the universe literally unfolds in front of your eyes. I think that'd be a cool way to, like, you know, go, so to speak. Like if I were to choose, I don't know if I wanted to bring a morbid perspective to that, but that'd be an amazing experience to have. I'll go there because I'm not coming out of the black hole unless it's a wormhole to another universe, which is real, and we'll talk about that. Well, that would be kind of cool, right? So who knows what's inside a black hole? We don't know. Nobody knows. So pause. That was a lot. But that's the significance of what the Schwarzschild metric predicts happens at the event horizon in terms of time. Now, we can take a step back and realize that this gets even stranger. Because once we're in the black hole, we keep going. It's not like, okay, I look out and the universe unfolded in front of my eyes and I stop. No, I keep going. Like I said, I would keep going. And what's inside? Well, the Schwarzschild metric tells us at least what's in the interior. For instance, if I plug in R equals 0.5 RSCH, what do I get? Well, I would get dt prime equals 1 minus RSCH over 0.5. RSCH, and quick math, and let's stick with the 80 years, but it doesn't matter what dt prime is. I get the square root of -1. which is impossible. We're not dealing with quantum mechanic wave functions here or imaginary momentums. This is taken literally as just impossible, which means it doesn't exist. So what does that mean? Well, here's where it becomes fascinating. Recall, where did we start? Here. We assumed we were at rest in space so that we would just have time dilation. I just wanted to isolate motion through time. I'm sitting on a rocket or a chair, and I just want to move through that fourth dimension of time, noticing my breath in a fun meditation and watch everything else move around me. So inside a black hole, or should I say inside the event horizon of a black hole, we assumed that dr is 0, and we got that that's impossible. So it's impossible to have a dr equal to 0 inside a black hole, which means it's impossible to be at rest inside a black hole in space. Inside RSCH, it's impossible for dr to equal 0. You must move through space inside a black hole. Does that make sense? That actually should make sense. Because no matter what, you can't sit still. I can't sit here and fire like some rocket boosters on a little pad and hang out and say, hey, I'm just going to hang out here. There's no force strong enough. Because light can't even escape. Light would be drawn. So light's trying to escape. It's like, we're going to see, it's like swimming up a current that's too strong, or swimming up a waterfall. Light says, ah! It's like walking up a down escalator. But you can't ever walk fast enough. That escalator is going one way toward the singularity. All futures point toward the singularity in space, where future now becomes a space, not a time. Let's look at that in more detail. Let's bring back the full metric. I'll do ds just for space-time. Let's do r equals 0.5. 1 minus r SCH over 0.5. C squared dt prime squared minus dr squared over 1 minus r SCH over 0.5. So I get what? Negative 1. This is negative 1. 1 minus 2. This is negative 1. So negative times negative, sorry. I keep forgetting the c squared. Plus dr squared. Take a moment and realize that this is the metric at this location. Now it's only at this location. What you can show pretty easily is that for any location inside a black hole, the event horizon of a black hole, that the dt becomes negative and the dr becomes positive. Why is that significant? Well, for this specific example, if I set dr equal to 0, I get the square root of a negative number, which is impossible. But remember, this is at r equals 0.5 RSCH. If I set dt equal to 0. I get that my motion through space-time is only through space. So what does this mean, friends? In our four-dimensional landscape right now, is it possible to not move through time? Meaning, in flat space-time, in flat space-time, dt prime equal to 0 is impossible. Right now, it's impossible to not move through time. This is called teleportation. Inside of a black hole, space and time switch roles. Showing that space and time are the same thing. Time is just another spatial dimension. Did that just sink in? Did that just like rip you apart? Where you can stop moving through time and move through space, which means that which compels you through time in flat space-time right now compels you through space inside a black hole. That all futures are in a spatial dimension inside a black hole. Whereas here, in our everyday life, all futures are in a temporal dimension. Does that mean you could freely move through time by choice? I'm going to move this way through time. I'm going to move this way through time. Just like you could move left or right through space, maybe you can move left or right through time inside a black hole. Maybe. I'll let you to think about that.